My name is Stephan Kister, and I'm working for Partec in Germany, company in HPC quantum computing. Right. So the first question is, so why do we need HPC with AI or quantum computing? And then I would like to go into the challenges of HPC and also the challenges of AI, supercomputers, and then we move into the quantum space later. So the next chart, please. So in the next chart, you can see, thank you. Yeah. In the next chart, you can see the challenges for HPC right now, because when I was grown up in the last century, right, I did my PhD in 1999, which was quite a long time ago. But in that time, every new year, new technology came up and we got a speed up, right? And the speed up was also described in the early or the late 60s by Morse, and it was called so-called Moore's law. So more things could be stacked on a chip, and at the end, the performance of a chip increased by that. And it was increased by every 2 years or every year. It was linear scaling, and you can see that here as well. That is exponential scaling because it is a logarithmic scale in the time of the top 500 teraflop, and it's the sum of all systems here, the blue points right now. And you see from the first or from the beginning of the top 500 list up to 2013, I would say we have this exponential scaling. But then you see also that there is a shift in this kind of line. So there is a new line that came up, which has a lower slope here after 2013. That means when you look, for example, into this average, the performance improvement, the 11-year average on the second axis here, which is this orange line here, is almost, let's say, a flat line until 2013. So there is only a smooth performance improve over the beginning of the top 500, but after 2013, it's going down. And that is something, that really challenges the HPC people, because you see that the supercomputer is not, let's say, getting new kind of performance by getting access to more powerful computer chips or putting more of them into a system right now. And that is really a big challenge, because we want to have more power with new systems, but we cannot do that with classical technology, CMOS technology right now. And that was the reason why the things that were used for AI were also introduced into the supercomputing world. The GPU cases is also a classical kind of technology which is integrated in these systems of top 500. This brings a little bit of, let's say, some kind of performance over pure CMOS CPU system. But at the end, if you remember the first chart, we still get this kind of decreasing performance over the years, even we use this kind of new kind of GPU technologies. We HPC are not using GPUs for AI, for the moment not, but for, let's say, powering classical systems with another kind of classical chip technology. I took also, let's say, for this kind of systems, so if we go from GPU systems, HPC, into our mind to other kind of AI supercomputers, so that it's purely powered by GPU. My statement is that the power consumption is becoming a problem, because we saw that already in the HPC world, and that is something what this diagram shows here. So there is the power consumption of the green 500, but I only took the first 250 systems. The reason is that we do not have power consumption in kilowatt for all 5 green 500 systems over the complete years. So we started with the green 500 list around 2013. And at the beginning, GPU systems were really only a few dozen. So there was, from the power consumption area, let's say a flat line. But then it was a steady growth from 2016 to 2021. More and more GPU power systems come into the top 500. That also means into this top green 150 out of 500 right now. And the third part, if you see here, there's also a step above that is the step 2022 to 2025, there was an explosion in adoption of these GPU accelerated systems. Around 200 accelerated systems by mid 2024 and about 300 systems then in 380 systems in mid 2025. And that brings the energy curve, even for the green 500 systems, to a level where I see when we are totally on the road of having just GPU powered system, the energy consumption is becoming a problem for local providers, for example, who can provide me enough power to bring these supercomputers for AI up and running without having damaging the power consumption also for the society, right? So we need new kind of power sources, if you remember, and that was really a crazy topic. That's the big hyperscale thinking about having smaller nuclear power plants near their new kind of factories they want to build with much more power consumptions that we have here. Around 350 is not, let's say, the scale they are thinking of. It's much, much more. I think that is really driving into a problem. So we have these classical technologies, HPC on the one hand, with the CMOS technology, which having a problem in performance by creating new kind of architecture or technology on bringing in that, even if we bring in more system into this kind of supercomputer will not help. And even if we bring GPU powered system into these supercomputers will not help, the power or the performance of the systems is decreasing. And that was the reason why we are thinking also about quantum computing, a third technology, to integrate in the future into HPC and AI systems. So co-locating and quantum computing is still a hybrid approach. So we have HPC and we have AI data center, and it is gaining attraction to bring quantum computer into that. So we can use, of course, the classical system still for pre and post processing. And then we're using just quantum for tackling the specific quantum suitable task, maybe in chemistry or specific optimization tasks, if there's a quantum advantage or not, or in machine learning, for example. Integrating HPC in quantum computing is not a question of bandwidth, I would say, because what is today, let's say, carried out on a quantum computer is very small because we do not have a big data load, because we do not have a quantum memory right now. So the quantum memory is missing. So we need to encode our data in circuits to encode the data to the quantum computer. But we can use low latency to have this kind of interaction between quantum computing and HPC. And probably there is a possible energy advantage of quantum computing. We cannot say that now for sure, but it seems so. If we have such problems and we can reduce the supercomputing power consumption footprint by using quantum computers, that would be, let's say, a fine step forward right now. Next slide, please. But quantum has also its challenges, right? We do not have a quantum computer who can assure us a quantum advantage for a moment. So we are struggling with qubit quality and scalability. You see this chart, which I took from a French guy. He published that in January 2025. And there you see on the x-axis, the average 2 qubit gate errors, and the other epsilon, the y-axis, is the number of physical qubits right now. And you see there are two rectangles here. There's one with shaded red, and that is the shaded magenta above this. So these are the typical areas where we can simulate a quantum computer on a classical computer. So for the moment, you can see what is below this 40 qubit area, we can simulate without any errors. And in this magenta, shaded magenta rectangle, this is the tensor network method. So we can also simulate at low error rates to hundreds of thousands of qubits with this kind of technology on a quantum computer. And you see all the dots with the different kind of quantum technologies we have today in place. And there's also this white space of this diagram. And that is the space where we must go to with our quantum computer hardware. Must move out of this area where we have a low error rate for the quantum qubits and that we have a reasonably high number or reasonably high physical qubits. There are different kind of technologies how to achieve this. We can use this physical kind of qubits with quantum error mitigation methods probably, and we will probably see some early quantum error correction codes which help us. But for the future, maybe in more than 5 to 10 years, we will definitely see these quantum error correction codes building these kind of logical qubits with these kind of low error rates that are necessary and to in a reasonable number amount of logical qubit that we need to solve, let's say, real problem and real use cases. We have quantum computing as a technology which have some promises, although we do not have this kind of advantage for the moment. We are just thinking already about how can we integrate this kind of technology into an HPC or a data center. And that is a problem from different angles, I would say, because the technology is so different from what we have in a classical supercomputing data center. Because there we have just racks, we have component-based systems, we have CPU nodes, we have storage nodes, we have network nodes, and we all bring that together in smoothly 19-inch racks that filled up great halls of compute power, I would say. And on the other hand, from the quantum computer, we have this kind of fridges, we have nitrogen we have to fill up, we have analog signals in our quantum computer. And that is not easy from this hardware perspective, just to integrate it into quantum computing center. I remember a talk from LSE, from Laura Schulz. It was at the DKRZ. And she said that for some reason they see in their quantum center when the S-Bahn is driving right away along their research center, that there is, let's say, impact of the QPUs at the end. So it is very sensitive, and we need special placement to bring these quantum QPUs near to a HPC or a data center right now. But it's also on this software. It is also at the software level, and the software level is, for example, that we have HPC, which is batch-driven. They use C++ or Fortran. On the other hand, we have quantum programming in these kind of frameworks, which is Qiskit or other Penny Lane SDK, where we use Python or Julia. And we have analog signals and no digital signals. So there are all different languages between the different personas, which is also a problem to bring these guys together so that it fits into a good solution at the end. So we need this bridging between from a high-level quantum computing SDK, which is integrated to some extent in a classical workflow, which is bringing that circuit, which is digitalized, into an analog signal and back this analog signal result signal back to the HPC system. Okay, so next slide, please. One example of how problematic it could be and the differences in thinking. If you are an HPC administrator, you are using a workload scheduler, for example, like Slurm, and the Slurm scheduling availability is about a minute. But on the other hand, if you're looking for superconducting quantum computers, the quantum gates are nanoseconds, but a quantum gate does not make a circuit. So we do have to do some shots on the superconducting QPU. So let one circuit move through the quantum computer, which is one shot, and we need at the end thousands of shots, which is here in microseconds. And then we are on a job level, which means these thousands of shots to have this job done on a superconducting system. We are in seconds. And if you then bring that into an application, maybe to have material science investigation, it could take you about 14 hours or 60 hours to do, let's say, the complete job at the end. Of course, you cannot stop an HPC supercomputer for the time waiting for the quantum computer coming back with the results. So there must be some changes to do to accept this from the application level. The other kind of quantum computers we have, so we have different technologies like ion trap or neutral hadrons. They have different kind of physical characteristics, and this has to be adapted as well if you want to use different kind of quantum computers in such an environment at the end. Okay, as I said, there should be already some kind of workflow for the classical solution in AI or HPC. So there's some pre-processing step, and then this is going into an HPC solver. And at the end, you're getting the application results. Now we want to build this kind of quantum solver, and we need this kind of API, which is bridging between the HPC system and the quantum computer, as I said before. There is one solution from Partec and the quantum machines, quantum electronic provider from Israel, which is called QBridge. But there are other things in the place in the meantime to do this kind of bridging. The problem is that we have different kind of technologies in the quantum electronic software stack, which is translating this digital signal to an analog signal and back and forth. And therefore, we need for the moment, as an integrator, as Bartek work, for example, different kind of APIs or specific APIs for a specific solution for the moment. So standardization is something that must happen in that field to make it easier to integrate a quantum computer in the future. Right. Next, please. I want to bring also one use case example with me. So that is an example the UK company Orca Computing does with a British oil company, and they use this quantum accelerated HPC AI solutions. Utilizing quantum classical Gen AI means in that area that quantum only brings a very, very specific and tiny piece of a whole classical workflow in here, right? So the generator is classical, the discriminator is classically, the data is also classic, but the lattice space that is created on this photonic quantum computer, which is Gaussian Bose and sampler, and that is something that brings this randomness from quantum to a use case like this use case, creating the so-called conformers or isomers of the QM9 molecule, right? So because it's a large molecule here, the molecule can rotate and the molecule can have a different structure. And all this belongs then to a different kind of energy for this kind of molecule. And of course, the oil companies, the pharma, and the chemical companies are interested in these kind of new conformers and isomers, which they do not recognize right now with the classical methods. And what they see here in this kind of use case was that the result of the conformers in the low energy area was a little bit better than the results with a classical lattice space or coming from a classical resource. It is not a side of quantum advantage, but I think it is a good direction into this. Using really some very simple thing from quantum, bring that into a hybrid workflow for HPC and AI solutions. And I want to close with what IBM has published a couple of weeks ago. And I cut out one of, let's say, these sentences. You could say, okay, it's a little bit about marketing, but I like the sentence quite well because they said that the users will deliver quantum advantage, and they talk also a little bit about what do they think is quantum advantage. Quantum advantage here is also cheaper, faster, or more efficiently than classical alone. I'm not sure about these cheaper and faster things, but I'm very sure about efficiently than classical alone. So by integrating these kind of different technologies, there can be an advantage for the users. And that is by the end of 2026, which is quite challenging. IBM is a big company and I was a long time there. Maybe they are able to do that in the future. And they close this sentence also that quantum serves as an accelerator for classical HPC. And that is also what I see. Quantum alone is not a solution. The same for HPC alone is not a solution. And AI supercomputer, maybe they are for a certain kind of time period from now to the next couple of years a solution, but not for the future because of this energy consumption that becoming more and more a problem. So we need some more efficient technologies working together for at the end for the best solutions. With that, I'm finished and I'm hoping I can answer some questions.